Hi, we are now looking at section 1.5 and this is about solution sets of linear systems. Well, we have been looking at solutions of linear systems since section 1.1. Here we are basically discussing there are two types of linear systems, homogeneous and non-homogeneous. What is the difference between them and how can we find the solutions in each case and how are the solutions related? That's what we are going to look at, and we are going to look at solutions in vector form, and also we can discuss the geometric description of these solutions. So what is a homogeneous linear system? A system of linear equations is called homogeneous if it can be written in the form Ax is equal to 0. What does that mean? It means when you multiply the solution x with the matrix A, we end up getting a 0 vector. And why would we get a 0 vector? Because you can see here A can be written as a vectors, columns of A represent the vectors A1, A2, up to AN. Then we multiply it with the 0 column vector and we end up getting a 0 as I have shown here. Now such a system will always have at least one solution, which is x is equal to 0. So it means this is always a homogeneous system is always going to be consistent. Now this x is equal to 0 is called the trivial solution. Okay? Any non-zero solution of the homogeneous equation is called the non-trivial solution. So if it is possible that we have more than one type of solution, so we can have for the homogeneous homogeneous system, we may have a solution which is non-zero. So not all of the entries in the vector are 0. So not a homogeneous system is always consistent. You have to remember this. Note that the homogeneous equation Ax is equal to 0 has a non-trivial solution. So when will it have a non-trivial solution? If and only if the system has at least one free variable. So if we have one free variable or more than one free variables, then we can expect non-zero solution or non-trivial solutions in the system. So non-homogeneous system, as we know, is Ax is equal to b, and it is consistent for some b. So there is a theorem how the two solutions of the two systems are linked. This is what this theorem is showing us. It says suppose the equation Ax is equal to b is consistent for some b. Okay, so there is a solution for some b, and let p be a solution. So it means there could be more than one solution, so we just pick one of them. Then the solution set of Ax is equal to p is the set of all vectors of the form W, which is equal to P plus T V. Well, there is an H subscript here, just to show that the VH is the solution of the homogeneous equation. So VH is a non-zero solution of the homogeneous equation. Well, it could be the 0, 0, 1 as well. So then we will not have this term, just this as our solution. Anyhow, so any solution of the homogeneous equation Ax is equal to 0, then P plus TV is called the parametric vector form. So when we write our answer like this, we have written it in a parametric vector form. So let's see how we do these problems. So the first one is saying determine whether the system has a non-trivial solution or not. So basically we just have to apply the row reduction, or we have to apply the row operations to the augmented matrix. So here is our augmented matrix. I may augment the zeros, or I could work only with the coefficient matrix. Now in the first row, in the first column. So this is our pivot position. So you'll use it to make the entries below the one or below the pivot to be 0. We multiply the row 1 by 2 and add in row 2. And then we multiply row 1 by -2, add into row 3. We end up getting first row is not changed, but in the second row I'll get a 0 here. Then I get a -7 because remember we are multiplying row 1 by 2, so 2 times -2 is -4, -4 plus -3 is -7, and then we get 2, and then we get 0. The same way, the third row gives us 0, and then it also gives us 0 over here, and then we're getting 3 and 0. Now, if we go by our rule, so we will now divide this, multiply the row 2 by 1 over 7, giving us also we can at this stage multiply the third row by 1 over 3 because we know we have to get a 1 here. So now you can see from here this is the echelon form. I can keep going and reduce it to the row reduce echelon form. Now it will be easier in this step, it will be easier to make the use the pivot in the third row, this pivot, and make these entries above 0 and then come back to the pivot in the second row. It will just save us some work and some time. So I will keep the third row as it is, make changes in the first and the second row. So I will multiply the third row by -3 and add in first row. And to make this quantity as 0, I will multiply the third row by 2 over 7 and add into the second row. So this will give me 0 and 0 here, and nothing else changes. So that is easier to do it. Now I can make this one, use this pivot and make the so now if we read the equations, you get x1 is equal to 0, x2 is equal to 0, x3 equal to 0. So we have the trivial solution. We have only the trivial solution or non-trivial solution. Same thing, now we have to look at this one and we start with the matrix. -5, -3, -2, 0, -3, -4, 2, 0. Now we don't have a 1 in the first position. So instead of multiplying by 1/5, I am going to see if I can somehow get 1 by using the multiple of another row. So if I multiply the second row by 2 and add into row 1, what will this give us? So it will give me -1, -11, and 2, and 0. The second row will stay as it is. Okay. So now I can make the 0 in the place of -3 over here. What do? I can multiply the first row by -3 and add in, or I could first multiply row 1 by -1. So now multiply row 1 by 3 and add into second row. So this is what I am getting. 1, 11, -2, 0 in the first row, and 0, 29, -4, 0 in the second row. So from, we can now divide by or multiply by 1 over 29. Now we write our equations. Well, I can do one more thing. I can go ahead and do the, instead of doing the back substitution, I would like to reduce it to the reduced row echelon form. So I can make this 11 a 0. So over here I have -4 over 29. When I do the calculations, I end up getting a -14 over 29. Now I can write the equation. So x1 from the first row, x1 minus 14 over 9 x3 equals 0. And from the second equation, I have x2 minus 4 over 29 x3 is equal to 0. From here, x1 is equal to 14 over 29 x3, and from the second equation, x2 is equal to 4 over 29 x3. So x3 is a free variable. And we often will write x3 equal to s or t, so that our solution becomes x1 is equal to 14 over 29t, x2 is 4 over 29t, and x3 is just t. So this is our solution. If you want, you can write it as a point. Actually, let's write it as a vector first. So in the vector form, our solution is now looking at this. Actually, if you recall the scalar multiplication, of vectors. So t is kind of a scalar which is being multiplied with each component. So it's the opposite of what we do in the definition. We are now taking t out, because if you multiply back, you will get the vector we have. So this is our solution. So sometimes we write our solution like this. So write the vector t outside such that t is a real number. Okay, so what does that mean? That means we can have a trivial solution. So it says if the solution exists, write it in parametric form. So this is the parametric form. Or this is the parametric form. Okay. So we say yes, the solution, there is non-trivial solution. Actually, there are more than one. Okay. Okay, again, determine if the system has a non-trivial solution. If the solution exists, write it in parametric form. So this is a single equation, so we can directly get the solution from here. So now there will be two free variables in this case. So which one? If any two could be, we can choose any two as free variables. Usually we pick the later variables as free. Instead of having x1 and x2 as free, we will say let x2 and x3 be the free variables. So, and let's say let x2 equal to s and x3 equals t. So I can write the equation. I have to now write x1 as a linear combination of x2 and x3. So I can write 10x1 equals 3x2 plus 2x3, or x1 equals 3 over 10 x2 plus 2 over 10 x3, or 0.3 x2 plus 0.2 x3. But then x2 is s, so I can write 0.3 s plus 0.2 t. So we have the situation, this is our x1, x2 is s, x3 is t. So when I write in vector notation, I get that is x1. Now x2 is s and x3 is t. Now what is this? Note here I wrote the x2 and the s and t under s and t in the first place, so that I can show you that we can write it as s plus 0t, and this can be written as 0s plus t, so that this is actually a sum of two vectors. So you can have 0.3 s and 0 into s, which is 0, plus now 0.2 t plus 0 and then t. When we take out the the parameters here. These are called parameters. So I can pull out the parameters. One left with 0.310 plus t into 2.201. So this, so what does that mean? What is this thing that we have here? This is a linear combination of these two vectors. One I am calling v1 and the other I am calling v2. So what is this geometrically? So geometrically, this will be the solution is a plane in R3 how the plane is, what is the plane consists of? That is, that contains v1, v2 and the 0 vector. So it is the plane, you can say, which passes through v1, v2 and 0, or which contains these. So this will be a plane which will pass through origin. So this is what, if you look at the previous one, this was only one vector and then we have a constant or a parameter, not constant, sorry, values change. So it's a parameter, so it can take any real value. So what is this? This is multiples of this vector. So remember, this represents a geometrically line in R3 passing through v1 and 0. I'll stop here and do the next example in the next video.